Okay, so here's part two, statistical mechanics and computational physics practice final exam. Okay, so number 8, ferroelectric material is modeled by Landau free energy. F of PT equals this entire, this is the function here. Part A, determine the equilibrium polarization P of T. So ferroelectric phase transition, equilibrium polarization, we're going to set this partial df dp equal to 0. So df dp, taking that partial derivative of f with respect to p, is alpha times the quantity t minus t sub c, p plus beta p cubed. Setting equal to 0, that's p times the quantity alpha times the quantity t minus t sub c plus beta p squared, that equals 0. So p is going to equal 0, or p squared is going to equal negative alpha times t minus t sub c over b. So p equals plus or minus square root of alpha times quantity t sub c minus t over beta, for t is less than t sub c. Okay, letter B, show that the spontaneous polarization appears below t sub c. So for t is greater than t sub c, t minus t sub c is greater than 0. So only p equals 0 is stable. So for t is less than t sub c, p equals plus or minus square root of alpha times the quantity t sub c minus t over beta. It becomes real. Therefore, spontaneous polarization appears below t sub c. C, determine the susceptibility above T sub C. So here, susceptibility for C above T sub C includes the electric field contribution. So F sub E equals F minus EP, then equilibrium. That's going to give us that alpha times T minus T sub CP plus B, P cubed minus E equals 0. For small e above T sub C, P is small, so ignore P cubed. Thus, alpha times T minus T sub C times P equals E. So P is going to equal, when we solve for that P, is E over alpha times the quantity T minus T sub C. Okay, and our chi here is that partial derivative of P with respect to E equals 1 over alpha times the quantity T minus T sub C. And this is Curie-Weiss behavior. Okay, letter D, describe the free energy for T greater than T sub C and T is less than T sub C. So for letter D here, free energy shape for T is greater than T sub C. The free energy has one minimum at P equals 0. For T is less than T sub C, P equals 0 becomes unstable. And two minima appear at P equals plus or minus P naught. Letter E, explain the physical origin of hysteresis in ferroelectrics. Okay, so what we could do here is right here, hysteresis occurs because ferroelectric domains can remain trapped in metastable orientations. Switching requires overcoming energy barriers associated with domain wall motion and nucleation. Okay, so that is number 8, and now we could move along to number 9. Okay, number 9. Oops, sorry, let me get this in focus. Okay, so consider the two-dimensional model we have here, Ising model. Okay, on a square lattice with the Hamiltonian given as this. Okay, for part A, derive the metropolis acceptance probability. So this is a Monte Carlo simulation of the Ising model. Metropolis probability for a triple spin flip. Okay, we have that S sub I approaching negative S sub I. The energy change is here. Delta E equals E sub new minus E sub old. The metropolis acceptance rule is P sub ACC equals the min of 1 comma E to the negative delta E over K sub B T. Okay, so letter B, explain detailed balance. So detailed balance requires pi of A, P of A going to B equals pi of B, P of probability, P of B going to A, where pi of a is proportional to e to the negative e to the sub a over k sub b t. This ensures the simulation samples the Boltzmann distribution. Okay, part C, the algorithm. So I'm just write this out in condensed form. Design a Monte Carlo algorithm to compute the magnetization as a function of temperature. So here would be a potential algorithm. So initialize an L by L lattice with random spins, to then choose a random spin, to then compute delta E for flipping it, then accept if delta E is less than 0. If delta E is greater than 0, accept with probability e to the negative delta E over k sub bt, and then we repeat for many Monte Carlo sweeps. We then compute the magnetization, m equals 1 over n for this summation here that we have for S of I, and then we repeat for different temperatures. Okay, so that's a condensed version. Part D, explain how finite size effects influence the measured critical temperature. So in a finite system, the phase transition is rounded, the magnetization does not become singular, and the measured critical temperature is shifted from the infinite system value. Okay. Part E, why does critical slowing down occur near the phase transition? Well, near the critical point, correlation lengths become large. Large correlated domains take many updates to decorrelate, so equilibrium becomes slow. Okay, so that is for number 9. And let's move on to number 10. Okay, so for number 10, let's see. Okay, number 10, I'll just get this a little more in focus. Okay, number 10. A Leonard Jones fluid is simulated using Monte Carlo methods. Okay. For part A, write the Leonard-Jones interaction potential. Okay, so this is canonical Monte Carlo simulation of liquid-gas transitions. Leonard-Jones potential is going to be this. This U of R equals 4 epsilon times the quantity sigma over r to the 12th minus sigma over r to the 6th. The r to the negative 12 term is repulsive, and the r to the negative 6 term is attractive. Okay. Part B and C, I switched them up. Sorry about that. B should be here. So B should be explain how periodic boundary conditions are implemented. So periodic boundaries. The simulation box is repeated in all directions. When a particle leaves one side, it re-enters from the opposite side. Distances are computed using minimum image convention. And now letter C. Explain how pressure may be estimated from simulation data. Pressure estimate, the pressure can be estimated from the virial equation right here, given here. Okay. Part D, explain how phase coexistence may be identified computationally. Well, phase coexistence can be identified by bimodal density distributions, formation of dense and dilute regions, equal chemical potential and pressure between phases in plateau regions and isotherms. And part E, discuss why equilibration becomes difficult near criticality. Near criticality, fluctuations occur over large length scales, interfaces form and dissolve slowly, causing long autocorrelation times. Okay, so that's number 10. That was canonical. A lot of this stuff is canonical standard, but very important. Moving along to number 11. Okay, so number 11, a classical molecular dynamics simulation is performed in a monoatomic liquid. Okay, derived for part A, Newton's laws for interacting particles. So again, this is a condensed form. This is a deterministic molecular dynamics problem, and this is a lot of canonical stuff, this one. Equations of motion for particles interacting via potential U, that m sub I, and then we have the second derivative of r sub I with respect to t, that equals F sub I. So the force is F sub I equals negative delta sub I U. Thus, we get that M sub I R double dot R sub I equals negative delta sub I times U. Letter B, explain the velocity of relay integration algorithm. The velocity of relay and algorithm given R of t, V of t, and A of t. Okay, R of t plus delta t equals this. R of t plus V of t delta t plus 1/2 A of t delta t squared. Okay, and then from here compute new forces and acceleration A of t plus delta t equals F of t plus delta t over m. Then we update the velocity V of t plus delta t equals V of t plus 1/2 quantity A of t plus A of t plus delta t close bracket times delta t. Okay, and now we go to letter C. Why is energy conservation important in microcanonical MD simulations? Okay, so here in microcanonical MD, N, V, and E are fixed. Good energy conservation indicates the time step is small enough and the integration is physically reliable. Part D, define the radial distribution function G of R and explain its physical meaning. Okay, so for part D, the radial distribution function G of R measures the probability of finding a particle at distance r from another particle relative to an ideal gas. G of R equals the local density at R over bulk density. Liquids show peaks in G of R, indicating short range order. Part E, describe how diffusion coefficients may be extracted from particle trajectories. Well, we use the mean square displacement here. Okay, and in 3D, the d equals a limit as t approaches infinity over 1 over 6t of that mean squared displacement. Okay, so that is number 11. Number 12. Okay. Let's see, number 12. All right. Number 12, is this in focus? Let's see. I'll read it here. Okay, we have a Brownian. Brownian particle obeys the Langevin equation. M dV dt equals negative gamma V plus eta of t, where eta of t is Gaussian white noise. Okay, so part A here, state the statistical properties of eta of t. Okay, so stochastic molecular dynamics, noise properties for Gaussian white noise. We have that expected value of eta of t that equals 0. So now we're going to add eta of t prime. That expected value there equals 2 gamma k sub b t delta, pardon my horribly drawn delta of that t minus t prime. Okay. Part B, determine the mean velocity. Take the average here in part B, at m d of that b, the expected value of the velocity dt. That equals negative gamma of expected value of the velocity. Solve for d dt of the expected value of the velocity, or average. So negative gamma over m times that mean expected value. So v of t, that mean expected value, equals v naught e to the negative gamma t over m. Okay. Part C, determine the long time mean square displacement. Okay. This is canonical. At long times, motion becomes diffusive. We have here that x of t minus x naught squared, expected value of that. That's 2 dt. Okay. Einstein relation gives d equals k sub bt over gamma t. So we're going to take this, that quantity x of t minus x naught squared, that expected value of that, that's going to equal 2 k sub bt over gamma t. And in 3D, it's going to be that expected value of that, the magnitude of r of t minus r of 0 squared. That's going to equal 6 ddt, and that's going to equal 6 k sub bt over gamma times t. All right, part D, explain the fluctuation dissipation theorem. Okay, so this is a condensed version for D and E. These will be condensed. The same friction coefficient gamma that dissipates energy also determines the noise strength. Thermal noise and damping must be related so the system equilibrates to temperature T. Part E compared deterministic and stochastic MD methods. So part E, deterministic MD, solves Newton's equations directly. Stochastic MD adds random and dissipative forces to model coupling to a thermal bath or solvent. Okay, so moving along now to number 13, that was 12. Okay, so we have a thin absorption layer, exchanges particles with a reservoir at chemical potential mu. Part A, construct the grand partition function here. Okay, so part A, this is grand canonical ensemble interfaces for a system exchanging particles and energy with a reservoir. Here, we're going to get this entire quantity, our xi equals these sigmas, these summations. Here, where beta is 1 over k sub b t. Okay, so this is canonical, part A. Part B, derive the grand potential we're given here for phi equals this negative k sub b t ln of xi. Okay, so grand potential is given. It's also commonly written as that. Phi equals u minus ts minus mu capital N. So that was, I should have, my apologies, I should have just said demonstrate or show, not derive, because that's not a formal derivation. Okay, part C, show the average particle number is obtained from this phi. So that average, and this is just a condensed version, this is average value of n equals 1 over beta. And then we take the partial here, that d xi du, d ln xi du, partial. And since that phi equals negative k sub b t ln xi, we get our average particle number is going to be that negative partial d phi d mu at TV. Okay, part D, explaining the connection between surface tension and interfacial free energy. For an interface of, for part D, for an interface of area A, the interfacial free energy contribution is F sub interface equals gamma A. Thus, gamma is going to be this partial dF dA at TVN. Surface tension is free energy per unit area. Part E, discuss why grand canonical methods are especially useful for interface problems. Okay, so interfaces often exchange particles with nearby bulk phases. Grand canonical methods naturally allow adsorption, desorption, density fluctuations, and phase coexistence. Okay, and now we have the last one, which is canonical, number 14. Okay, so 14, a molecular system has multiple metastable conformations separated by energy barriers. Part A, explain why ordinary MD may fail to sample all relevant configurations. So the computational free energy landscapes. So this is canonical, important stuff. Part A, ordinary MD can become trapped in metastable states if an energy barrier satisfies delta F is much larger than k sub bt. Then transitions occur rarely within accessible simulation time. Part B, describe umbrella sampling. Umbrella sampling adds a bias potential, often harmonic. U sub bias of Q equals K over 2 times the quantity Q minus Q naught squared, where Q is a reaction coordinate. This forces the system to sample otherwise rare configurations. Part C, define a reaction coordinate. A reaction coordinate is a reduced variable that tracks progress between states. Examples include distance, angle, density, magnetization, and molecular conformation. Part D, explain how free energy profiles are reconstructed from bias simulations. So part D here, the bias probability is B sub bias of Q is proportional to E to the negative B of that quantity times the quantity F of Q plus U sub bias of Q. Thus, F of Q equals negative K sub BT ln P sub bias of Q minus U sub bias of Q plus constant. So f of q equals negative k sub b t ln p of q plus c. And we could say multiple bias windows are combined to reconstruct the full free energy profile. And letter E, discuss one advantage and one limitation of enhanced sampling techniques. Okay, one advantage, enhanced sampling allows rare transitions in barrier regions to be explored. Limitation, results depend strongly on choosing a good reaction coordinate and sufficiently overlap between sampling windows. Okay, so sorry if I mispronounced anything or went too fast, but you have this as a reference. And thank you very much, and have a great day.